Problem number 2 on the optimization worksheet, we're trying to figure out if you have a semicircle that has a radius of 4, so here we have a point 0.04, and we inscribe a rectangle inside of this semicircle. What's the area of the largest rectangle that we can inscribe? So the bottom of the rectangle has to be on the diameter of the semicircle. So one kind of major roadblock here is, well, how do we express this semicircle in terms of a function? Well, semicircle has an equation, y equals radical 16 minus x squared. So in general, the semicircle has y equals the square root of r squared minus x squared. And r, in this case, being the radius being 4, that's why we have a 16 right there. So that's the semicircle equation. And if we label our rectangle from the origin to the right edge of the rectangle as having a length of x, then that would mean that the height of the rectangle has a value that's the same value as the y coordinate of that point right there. You go over x and up y. Well, y is radical 16 minus x squared. So that's what the height of this rectangle is. And so then we could figure out, well, what's the area of the rectangle? Well, leads me to the steps that we want to take when we're trying to optimize something. Well, first of all, you have to come up with a function in terms of one variable. Well, the function that we're trying to actually find a max or a min for, largest means max. So we're trying to maximize the area, so we have to come up with an equation for the area in terms of one variable. And the area, once we label our rectangle correctly, the area then would be the length times the width, or base times the height. Well, if that's x from there to there, then this would have to be another x from here to here. So therefore, the length of the base, or the length of the rectangle, is 2x. Well, what's the height of the rectangle, or the width, whatever? What's the second dimension? Well, the second dimension is what we already said. That's the radical 16 minus x squared. So the first step in being successful in solving an optimization problem is to come up with an equation or a function that you're trying to find an extreme value for. That's the first step. And then it all goes back to the same stuff that you guys have been doing, and that is find the maximum value. Well, okay, how do we find a maximum value? Where do maximum values occur? Well, extreme values occur when the derivative is we're at critical points and endpoints. So that's the bottom line. Extreme values occur only at critical points and endpoints. How do we find critical points? Well, we find critical points, first of all, by taking the derivative and setting the derivative equal to 0. So we have to find the derivative of this function. This is the product of two functions, so we have to use the product rule. So we have the first function, 2x, times the derivative of the second. Well, that's 1/2 times 16 minus x squared to the negative 1/2 times multiply by the derivative of what's inside, that's negative 2x. That's the first part. That's the first times the derivative of the second plus the second, which is radical 16 minus x squared, times the derivative of the first. Derivative of the first, we consider the first being 2x. The derivative of 2x is 2. So here we have our derivative. Well, it's kind of a very complicated looking derivative right now, but let's see if we can simplify it a little bit. So the 2's are going to cancel. We have this x here, and we have this negative 2x here. So we end up getting negative 2x squared up on top. And then down on the bottom, we have radical 16 minus x squared. That's the first thing. That's got the x, got the negative 2x, so we've got all that. And then we have a plus 2 times the square root of 16 minus x squared. It's still more complicated than we want it. What we want to do is we want to get it down to one fraction. And let me move this all the way over here so that we can have a little bit more room. And we're going to get a common denominator. So we have negative 2x squared over radical 16 minus x squared. Then we have a plus 2 radical 16 minus x squared. And then we have to multiply top and bottom by radical 16 minus x squared. And that is the secret right there to getting a common denominator, but then simplifying the derivative. And again, this is a prime of x. So the derivative of the area in terms of x. So we get negative 2x squared and then plus 2 times, when you multiply the two radicals together, the radical symbol goes away. And we get that over our denominator, 16 minus x squared under the radical. And then we get equals, let's see, negative 2x squared plus 32 minus 2x squared again over I'm going to put dot, dot, dot for the denominator. I don't want to keep writing that. And then we have equals, let's say, negative 4x squared plus 32. Okay, that's our numerator simplified. We could factor out negative 4. And then we have the square root of 16 minus x squared. All right, so that's our derivative. That's what we're going to work with now, and we're going to set it equal to 0 because we want to find our critical points. And our critical points are going to be when a prime equals 0, so a prime equals 0, when the numerator is 0, and that's negative 4x squared plus 32 equals 0. And so if we divide through by negative 4, let's say, we have x squared, be careful here, minus 8 equals 0. So we divided everything by negative 4. Did we do that right? Negative 4, cancel 32 minus, yeah. So we have x squared equals 8. So x equals plus or minus 2 radical 2. Square root of 8, 2 radical 2. So that's what x is. But we could see we already labeled x on the diagram as being a positive number. And so if x equals 2 times the square root of 2, we're trying to find the area of the largest rectangle. Well, okay, so we're going to have to do our a prime test. But let's just continue to try to find our other critical points. A prime does not exist when radical 16 minus x squared equals 0. So when the denominator of the a prime is 0, a prime doesn't exist. So if you're thinking about this, that would be when x squared equals, when x equals 4. So if x equals 4, then think about it. If you look at the diagram, if x equals 4, then we're not going to have the height to the rectangle because we have all the way over here, there's no area. So if x equals 4, the area is 0. So that's going to definitely be a minimum, and that's going to be our endpoint anyway. So if we use a little bit of logic, we know for sure that the endpoint's 0. If x is 0, we have no area. And if x is equal to 4, we have no area. So those are boundaries for what the x could possibly be. X can't be bigger than that, because if x were bigger than 4, then the rectangle would be outside of the semicircle. So that's not allowed. That's not okay. But 2 radical 2 is in here somewhere. 2 radical 2 is a little bit bigger than 2. So it's in there. And so we have to figure out, well, what's going on with the derivative? Well, this is our a prime test. A prime test. In between 0 and 2 radical 2, certainly 1 could be a good test value. If we look at the derivative right here, put in a 1, we get negative 4 plus 32. That's a positive number. Certainly the denominator is going to be positive, so we have positive. If we put in a number like, let's say, 3.9, well, for sure, somewhere in here we're going to get a negative. 3.9, you can put in that, and then you can get negative 3.9 squared. That's certainly going to be, it's going to be a bigger negative number than 32. So as long as we get greater than, or less, I guess less than 32, less than negative 32, then this whole thing is going to be a negative number. So therefore, the numerator is going to be negative everywhere in this interval. So the a prime is positive. That means that a is increasing, and then a prime is negative. Therefore, a is decreasing. And so therefore, we have a max. And so when x is equal to 2 radical 2, the area of the rectangle is at a maximum value. What is the area? It says, so that's the next step is, well, answer the question. So we found the value of, or we did the a prime test, and so therefore we found when a is increasing and a is decreasing, and we found minimum values for the area when x is 0 or 4, and we found an absolute maximum value when x is 2 radical 2. But it's not asking for that. It's asking for what is the area of that largest rectangle. Well, the area of the largest rectangle then would have to be related to when x is equal to 2 radical 2. And the rectangle, remember, has the a of x. If we look back up here, a of x is right here. So we already defined the area of the rectangle based on x. So now we're just going to plug in at 2 radical 2. So it's 2 times 2 radical 2 multiplied by 16 minus 2 radical 2 squared. And I'm confident you can do this part, but I want to see it all the way through to the end. 16 minus, now 2 radical 2 squared. Be careful here. 2 squared is 4. Radical 2 squared is 2. So we have radical 16 minus 8. So radical 8 times 4 radical 2. And then we have 4 radical 2 times 2 radical 2. And therefore we have 8 times 2, and we have 16. So 16 is the area. And do we have units on this one? I didn't write down if we had units. So if we had units, we'd have square units or whatever the units are, inches, centimeters, whatever. But 16 is the answer for number